Imagine you buy a brand new car. You drive it home, park it in the garage, and for the next 10 years you never, not once, crawl underneath it with a grease gun. Not because you're neglecting it, because the car does it for you, every single mile, automatically, while you drive. That sounds like something a modern electric vehicle engineer might dream up in a Silicon Valley whiteboard session, except engineers figured this out before the interstate highway system existed, before power steering was standard, before most Americans even had a television in their living room. The world had decided that greasing a car was just part of owning one, a ritual, a cost of doing business with internal combustion. Every few thousand miles you pulled into a service station, a mechanic slid under your chassis with a grease gun and manually pumped lubricant into every joint, every fitting, every pivot point holding your car together. There were sometimes more than 30 of those points on a single vehicle. It was slow, it was messy, and more often than not, it was skipped entirely. Because here's what nobody wanted to admit out loud: most drivers never actually did it. And when they didn't, the consequences were brutal. Chassis joints, the ball joints, the tie rod ends, the kingpins, the steering linkages, they'd run dry. Metal would grind against metal, micron by micron, until parts that should last a decade wore out in 2 years. Steering became sloppy, suspension components failed without warning. In the worst cases, drivers lost control entirely on roads that were barely safe to begin with. The problem wasn't ignorance, the problem was human nature. Maintenance that's invisible, that happens underneath a vehicle most owners never look at, is maintenance that gets deferred, then forgotten, then discovered far too late, usually at the worst possible moment. Engineers understood this. They'd understood it for years. The question wasn't whether automatic chassis lubrication was a good idea. The question was whether anyone could actually build something that worked, a system compact enough to hide inside a production vehicle, robust enough to survive years of road vibration and temperature extremes, and precise enough to deliver exactly the right amount of grease to exactly the right places at exactly the right time. That's not one engineering problem, that's about 15 of them stacked on top of each other, and one company decided to solve all of them at once. What they built wasn't a gimmick, it wasn't a concept car feature that never saw a production line. It was a fully engineered, mechanically elegant system that quietly ran underneath millions of vehicles, doing its job without a single driver ever thinking about it. A miniature pump, a network of copper tubing thinner than a pencil, a metering system so precise it measured lubricant in fractions of a cubic centimeter. It worked, brilliantly. So why did everyone eventually abandon it? The answer starts, like most great engineering stories, not with a solution, but with a single engineer staring at a problem nobody else wanted to touch. By the late 1940s, the American automobile industry was in a strange place. The war was over. Factories that had been stamping out Jeeps and military trucks were now cranking out family sedans as fast as they could build them. Demand was explosive. Consumers had money, optimism, and an appetite for anything that felt modern. Car companies responded the only way they knew how, by making vehicles bigger, faster, and more powerful. Nobody was thinking about what happened underneath, but a small team of engineers at Bijur Lubricating Corporation had been thinking about almost nothing else for over 2 decades. Bijur wasn't a household name. They weren't building engines or designing body panels. They were specialists, a company obsessed with one narrow, unglamorous corner of mechanical engineering, getting lubricant from one place to another, reliably, under pressure, in hostile environments. They had built systems for machine tools, for industrial equipment, for locomotives. They understood viscosity, flow rate, pressure drop, and metering tolerances the way a watchmaker understands gear ratios, and they had been watching the automotive industry make the same mistake over and over again for years. The mistake wasn't malicious, it was structural. Vehicle manufacturers knew chassis lubrication was critical. They published maintenance schedules. They trained dealership mechanics. They designed increasingly accessible grease fittings, small nipple-shaped ports called zerk fittings, named after their inventor Oscar Zerk, that let a mechanic with a grease gun snap on and pump in lubricant in seconds. It was a genuine improvement over what came before, but it still required a human being to remember, to schedule, to actually do the work. And humans, as any engineer will tell you, are the least reliable component in any system. Bijur's engineers ran the numbers. A typical passenger car of that era had somewhere between 28 and 44 individual lubrication points across the chassis. Each one needed to be serviced every 1,000 to 2,000 miles under normal driving conditions. That meant for every 10,000 miles driven, a conscientious owner was looking at somewhere between 5 and 10 complete chassis lubrication services. Each service, done properly, took a trained mechanic 20 to 30 minutes. Most owners weren't doing it anywhere near that frequently. Industry surveys from the period suggested the average driver was lubricating their chassis at barely half the recommended interval, if that. The math was unforgiving. Under-lubricated chassis joints wore at roughly 3 to 4 times the normal rate. A kingpin designed to last 80,000 miles might fail at 25,000. A tie rod end meant to outlast the vehicle could become dangerously loose in under 3 years of normal use. The engineers at Bijur looked at those numbers and made a decision that would define the next 2 decades of their company's existence. They weren't going to remind drivers to lubricate their chassis. They were going to make it so the car never needed reminding at all. But to do that, they had to solve a problem that had stopped everyone else before them cold. The core challenge sounds deceptively simple when you say it out loud. Build a pump, connect it to all the lubrication points, run it automatically while the car drives. Done. Except nothing about it was simple, not even close. The first obstacle was grease itself, not oil, grease. There's a fundamental difference that matters enormously here. Oil is a liquid. It flows freely, responds predictably to pressure, and moves through small passages without complaint. Grease is something else entirely. It's oil that's been thickened with a metallic soap compound, typically lithium or calcium-based, until it reaches a semi-solid consistency somewhere between petroleum jelly and soft butter. That thick consistency is exactly why chassis joints need it. Unlike oil, grease stays where you put it. It doesn't drain away. It forms a protective film that clings to metal surfaces even under shock loads, even when a joint sits idle for weeks. But try pumping it through a narrow copper tube at low pressure and you'll discover the problem immediately. Grease doesn't want to move. It has what engineers call high apparent viscosity, a resistance to flow that changes dramatically depending on temperature. On a warm summer afternoon, chassis grease behaves reasonably. Push it hard enough and it moves. But on a cold January morning in Minnesota, that same grease becomes almost stone-like. Trying to force it through a thin tube under those conditions is less like pumping fluid and more like trying to push concrete through a garden hose. Every previous attempt at automatic chassis lubrication had collided with this problem and stopped. Some systems used heat to thin the grease before pumping. The heat sources were unreliable and added dangerous complexity. Some used extremely high pressure to force cold grease through the lines regardless. The pressures required were so extreme that fittings failed, tubes cracked, and joints received massive grease dumps rather than controlled doses, which created its own set of problems, blowing out seals and contaminating brake components. Nobody had found a way to move the right amount of grease to the right place at the right time across the full range of temperatures a production vehicle would actually encounter in real-world use. Bijur's engineering team approached it differently. Instead of trying to fight grease's physical properties, they decided to work with them. The breakthrough in sight, and it sounds almost embarrassingly obvious in hindsight, the way all genuine breakthroughs do, was that they didn't need to pump grease continuously. They needed to pump it in precisely timed, microscopically small pulses, tiny doses, almost homeopathic in their smallness. Each lubrication event delivered less than 1/10 of a cubic centimeter of grease per fitting. Not a generous slug, not a pressurized blast, a whisper. At that scale, even cold, stiff grease could be moved through thin copper lines without requiring the kind of pressure that destroyed fittings and blew seals. The dose size wasn't chosen arbitrarily. It was the result of extensive tribological testing, the science of friction, wear, and lubrication between moving surfaces. Bijur's engineers mapped exactly how much lubricant each joint type consumed per mile of operation under varying loads. A kingpin under cornering stress needed a different dose frequency than a tie rod end on a straight highway. They built those differences into the system's metering valves, small spring-loaded distributors that parceled out each grease pulse to its designated fitting with mechanical precision. It was, in essence, a mechanical pharmacist, measuring out exactly the right prescription for every joint in the chassis every few miles, without the driver ever knowing it happened. But a system that precise raised an immediate new question. What was going to drive the pump? Power sources are never free. Every engineer knows this. Tap into the engine to run your system and you're adding parasitic drag, stealing horsepower the driver paid for and converting it into something they'll never notice. Tap into the electrical system and you're adding load to a generator that, in the late 1940s, was already borderline adequate for the demands being placed on it. Add a dedicated motor and you've introduced a component that can fail independently, taking the entire lubrication system down with it at the worst possible moment. Bijur's engineers considered every option, and then they picked the one that sounds at first almost laughably low-tech. They used the speedometer cable. Every vehicle of that era had one, a flexible mechanical cable running from a gearbox-mounted drive gear all the way up through the firewall to the speedometer on the dashboard. It spun continuously whenever the vehicle was moving, its rotational speed directly proportional to road speed. It was already there. It was already turning. It required no additional electrical load, no parasitic engine connection, no dedicated motor. It was, in the language of engineering, an elegant parasitic tap, borrowing a tiny fraction of energy from a system that had energy to spare. A small worm gear drive intercepted the speedometer cable's rotation and converted it into pump strokes. The faster the vehicle moved, the faster the pump cycled. The slower it moved, the slower it cycled. At highway speeds, the system might deliver a lubrication pulse every few miles. In stop-and-go city driving, where joints worked harder under constant steering and suspension movement, the lower vehicle speed naturally reduced pump frequency, but the shorter intervals between pulses kept cumulative lubrication surprisingly consistent. It was a self-regulating system built entirely from mechanical logic, with no sensors, no electronics, no control modules, just physics, doing exactly what physics does when you set it up correctly and get out of the way. The pump itself was a masterpiece of miniaturization. The entire assembly, reservoir, pump mechanism, pressure relief valve, and primary distribution block packaged into a unit roughly the size of a large hardcover book. It mounted to the firewall or inner fender, connected to a reservoir holding approximately half a pound of chassis grease. From that central unit, copper tubing, typically 3/16 of an inch in diameter, ran to every lubrication point on the chassis, following the body contours, clipped neatly to frame rails, branching outward like a circulatory system. Because that's exactly what it was, a circulatory system. The pump was the heart. The copper lines were the arteries. The metering valves at each fitting were the capillaries, ensuring each joint received its precise share regardless of its distance from the pump or the resistance of its individual line. A fitting close to the pump and a fitting at the far end of the rear suspension received identical doses. The engineering required to achieve that consistency across a branching network of different line lengths and resistances was, by itself, a significant technical achievement. General Motors recognized what Bijur had built. So did Chrysler. Within a few years of the system's commercial introduction, it began appearing as a factory-installed option on vehicles ranging from Buick Roadmasters to Chrysler New Yorkers to a staggering variety of commercial trucks and fleet vehicles, where chassis maintenance costs were a genuine operational expense that company accountants tracked with brutal attention. The system even earned a name that customers could ask for by name at the dealership. Bijur called it the Zentralschmierung in their European markets, central lubrication. In America, it was marketed with characteristic mid-century confidence simply as automatic chassis lubrication. Fleet operators loved it immediately and without reservation. The numbers told the story. Trucks equipped with the system showed chassis joint wear rates reduced by as much as 60% compared to identically operated vehicles on manual lubrication schedules. Kingpin replacement intervals stretched from 60,000 miles to well over 100,000 in controlled fleet comparisons. For a company running 50 delivery trucks, the reduction in maintenance downtime alone justified the system's cost within the first year of operation. The engineers had solved the impossible problem. They had built something that genuinely worked, and that's precisely when things started to get complicated. Success in engineering rarely arrives clean. It usually comes wrapped in a new set of problems that nobody anticipated, because the old problems were so consuming that nobody had the bandwidth to look further down the road. Bijur's automatic lubrication system was no exception. The first complication wasn't mechanical, it was human. Specifically, it was the service industry built around manual chassis lubrication, an entire economic ecosystem that had grown up around the grease gun and the service pit. Dealership service departments charge for chassis lubrication as a routine line item. Independent garages made consistent money on it. The quick lube industry, which was just beginning to establish itself as a distinct business category in the early 1950s, had built its entire value proposition around the idea that cars needed regular professional attention underneath. An automatic system that eliminated that need wasn't just a technical innovation, it was an economic threat. The resistance wasn't always explicit. Nobody stood up at an industry conference and said the words out loud. But fleet managers who tried to order factory-installed automatic lubrication on new vehicles sometimes found the option curiously difficult to specify. Dealerships that received vehicles equipped with the system occasionally found reasons to recommend supplemental manual lubrication anyway, charging for a service the system had already rendered unnecessary. The friction wasn't mechanical, but it was very real. Bijur's engineers, meanwhile, were dealing with friction of a more literal kind. Field reports from early production installations began surfacing a problem they hadn't fully anticipated in bench testing. The copper tubing that carried grease from the central reservoir to the chassis fittings was, by necessity, routed through an extremely hostile environment. Underneath the vehicle, temperatures swung from well below freezing to over 200 degrees Fahrenheit near exhaust components. Road debris struck constantly. Chassis flex during cornering and over rough surfaces created continuous mechanical stress at every bracket and clip point. Most of the tubing held up fine, but in vehicles subjected to particularly severe use, heavy trucks on unpaved roads, delivery vehicles in northern climates where road salt attacked every exposed metal surface, hairline fatigue cracks began appearing in copper lines at stress concentration points. The cracks were small. The grease loss was initially minimal, but a system that leaked, even slowly, was a system that eventually ran dry, and a system that ran dry was worse than no system at all because it gave the driver a false sense of security while delivering nothing. The engineering response was methodical. Bijur's team redesigned the tubing mounting brackets to reduce stress concentrations. They introduced armored sections of tubing in high-risk areas near exhaust components and suspension pivot points. They added a reservoir sight glass, a small transparent window in the grease reservoir, so drivers or mechanics could verify at a glance that the system still had lubricant. They reduced the recommended refill interval from 10,000 miles to 7,000 in severe service applications. Each fix was sound, each fix worked, but each fix also added cost. And cost in the American automotive market of the 1950s was a conversation that never ended well for complexity. Because something else was happening simultaneously, something the automatic lubrication engineers couldn't fix with better tubing or smarter metering valves. The vehicles themselves were changing rapidly, dramatically, in ways that made the engineering challenge of automatic chassis lubrication significantly harder with every new model year. Ball joints were replacing kingpins as the primary front suspension pivot in American passenger cars. Kingpins were large, robust, simple, forgiving of the kind of metered grease doses Bijur's system delivered with such precision. Ball joints were smaller, geometrically complex, and significantly more sensitive to both underlubrication and overlubrication. Their internal geometry created pressure differentials that could actually force grease back through a metering valve if system pressure wasn't carefully managed. The metering valves that had worked beautifully on Kingpin suspensions needed complete redesign for ball joint applications. Simultaneously, rubber-isolated suspension bushings were replacing metal-on-metal pivot points across the chassis. These bushings needed no lubrication at all. In fact, petroleum-based grease actively degraded the rubber compounds used in their construction. A system designed to lubricate everything it touched now had to learn to selectively avoid certain components entirely, or risk destroying the very parts it was meant to protect. The engineers were no longer maintaining a stable target. They were chasing a chassis architecture that reinvented itself every 3 years. They kept chasing. But the industry wasn't waiting for them to catch up. By the early 1960s, the automatic chassis lubrication system was fighting a war on 3 fronts simultaneously. Engineering complexity was rising, production costs were climbing, and the automotive industry had found what it believed was a simpler answer to the entire problem: sealed for life. Those 3 words became the dominant philosophy of chassis engineering in the 1960s, and they effectively pulled the ground out from under everything Bijur had built. The concept was straightforward. Instead of designing joints that needed periodic lubrication, engineers would pack them with a lifetime supply of grease at the factory, seal them permanently with rubber boots, and declare the problem solved. No fittings, no service intervals, no grease guns, no automatic systems, no copper tubing, no metering valves. Just a sealed joint that was supposed to last the life of the vehicle without ever being touched. It was, on paper, an even more elegant solution than automatic lubrication. It removed the maintenance requirement entirely rather than automating it. In practice, it was a compromise dressed up as a breakthrough. Sealed ball joints of that era lasted reasonably well under normal conditions, but the rubber boots that protected the grease packed inside were vulnerable to road debris punctures, to ozone degradation, to the simple mechanical fatigue of millions of articulation cycles over years of use. Once a boot cracked or tore, contamination entered the joint immediately: grit, water, road salt. The sealed grease that was supposed to last forever turned abrasive within weeks. The joint that was supposed to outlast the vehicle could fail catastrophically in months, but that failure happened slowly, invisibly, and usually well outside the warranty period, which meant it was somebody else's problem by the time it became obvious. Automatic chassis lubrication never disappeared entirely. It retreated from passenger cars and found a permanent, thriving home in the applications where it had always performed best: heavy commercial vehicles, construction equipment, agricultural machinery, transit buses, long-haul trucks. Anywhere that downtime was expensive, maintenance access was difficult, and the consequences of joint failure were severe. In those markets, automatic lubrication systems never went out of fashion because the economics never stopped making sense. Walk into a Caterpillar dealer today. Look at the service documentation for a modern highway coach. Examine the maintenance specifications for a city transit bus. Automatic chassis lubrication is still there, more sophisticated than Bijur's original system, driven by electric pumps rather than speedometer cables, controlled by programmable timers rather than mechanical drives, monitored by sensors that can flag a blocked line or low reservoir before a single joint runs dry. The fundamental architecture, central reservoir, distribution network, metered doses at each lubrication point, is unchanged in its essential logic from what those engineers figured out 70 years ago. The passenger car world eventually discovered that sealed for life had its own limitations. Modern vehicles have returned quietly and without much fanfare to serviceable chassis components. Greasable ball joints and tie rod ends are now marketed as premium upgrades in the performance and heavy-duty aftermarket. The logic that drove Bijur's engineers in the first place, that periodic, precise lubrication extends component life dramatically, turned out to be as true in 2024 as it was in 1948. It was never wrong. It was just ahead of what the market was willing to pay for and behind what the market was willing to maintain. That's the tension that runs through the entire story of automatic chassis lubrication. It was a system that worked, genuinely, demonstrably, measurably worked. It solved a real problem with elegant engineering, reduced wear rates by margins that fleet operators documented in black and white accounting records, and delivered on every promise its engineers made for it. It wasn't abandoned because it failed. It was abandoned because the industry found something cheaper, even if cheaper turned out to mean something different than better. The engineers at Bijur understood something that took the broader industry another generation to fully appreciate. The most dangerous maintenance interval isn't the one that's too short. It's the one that never happens at all. Automated, invisible, relentless attention to the parts of a machine that nobody ever sees, that's not over-engineering. That's just honesty about how mechanical systems actually survive contact with the real world. There's a copper tube somewhere beneath a 1957 Buick Roadmaster sitting in a collector's garage, still tracing its careful path from a firewall-mounted reservoir to a kingpin fitting on the front suspension. The grease inside it has long since hardened into something closer to wax. The pump hasn't turned in decades, but the system is still there, complete, intact. A mechanical argument made in metal and engineering precision for a philosophy that the industry walked away from before it fully understood what it had. The problem was obvious, the solution was brilliant, and somehow the world forgot it ever existed, until now.